Welcome! In this video about bioenergy, we will examine the role of critical raw materials in the efficiency with which biomass can be converted into biofuel, heat, or electricity. You will learn about the following topics in this video. Basics of biofuel to electricity conversion technology. Basics of thermochemical and biological processes for biomass to biofuel conversion. Explanations on the increased efficiency due to the addition of CRM in bioenergy conversions. Edison's power plant was commissioned in 1882 on Pearl Street, New York City, to provide electricity to a community. In this process, the combustion of coal, a fossilized biofuel, is driving electric power generation through 100 kilowatt dynamos. The first step in this process is the combustion of coal to produce heat. As we learned previously, the critical raw materials contained in the fuel end up in the ash with the waste products carbon dioxide and water vapor. The X, Y, and Z indicate the balancing of the stoichiometric molar ratio. Then as a second step, the heat and the gaseous carbon dioxide and water vapor are converted into mechanical motion or work. The internal combustion engine, invented by Nicolaus Otto, added the option to use pressure and volume diagrams to convert vertical motion of compression-decompression cycles into rotational work that could drive a car. Then for the transition from work to power, the rotational movement could be used to drive an electromagnetic generator and/or a steam turbine. However, after the extraction of work, the waste products, including the CRM, would remain and heat is dissipated to the environment. To acquire more control over the generation of undesired byproducts, thermochemical processes could be used. In a simplified form, biomass is dropped into a thermochemical reactor and exposed to a countercurrent flow with limited amounts of oxygen and a reforming agent, in this case water. Some biomass is combusted, generating heat, while consuming all remaining oxygen. This generates a high-temperature oxygen-free zone where gasification and pyrolysis catalyze the conversion of raw heterogeneous organic feedstock in a relatively homogeneous gaseous fuel, also known as syngas. Waste products can be collected in a relatively controlled manner. The addition of catalyst enhances the gasification rates and may increase the hydrogen yield. However, the bottom line is that although nickel and group 8 metals are chemically most effective, the process can run at lower efficiency with low cost or no catalyst at all. The generalized reaction equation of gasification using steam as gasification agent is presented here. But the reaction can also be completed using carbon dioxide as gasification agent, both using heat and either CRM or non-CRM catalyst. Also here, the residual ash, tar, and char contain once more the original CRM from the plant-based material. The biological alternative to combustion is used in organic wastewater treatment, in processes also like composting. Microbes use biomass and oxygen for respiration. Some low-temperature heat, up to 70-80 degrees centigrade, is generated, but the process also yields new microbial mass and carbon dioxide. Sometimes, trace elements are dosed to stimulate microbiological growth, similar to plant cultivation, and end up in the microbial sludge. As microbes catalyze the process, while no additional heat is required, the reactor design can be more simple. Microbes can be considered ambient temperature self-repairing catalysts and are known to rely on enzymes. Through the use of metal cofactors, the amount of CRM needed for catalyzing a conversion is reduced to a minimum. This table shows various enzymes and their metal cofactors known for anaerobic microorganisms. Here, the aerobic biological conversion is shown. It should be noted that stoichiometrically the mass balance is similar to the thermochemical process. However, the elements contained in the biomass should be deduced from the product side. By ensuring oxygen cannot enter in the bioreactor, the biochemical energy contained in the organic feedstock is now more efficiently transferred to the reduced end product, a cleaner gaseous fuel of CH4 and CO2. Alternatively, the bioconversion process can be directed to the production of energy-rich liquid end products like diluted ethanol. In both cases, while the CRM remains inside the microbes and can be used again. For anaerobic biological conversions, in terms of reaction stoichiometry, less energy is available for the microbial growth, due to which they reproduce less. Regarding end products, stoichiometrically, 1 mole of glucose will be transformed into 3 moles of methane and 3 moles of carbon dioxide. Although water takes part in the reactions, it is not always shown, as it is also the solvent. For calculating the theoretical biogas potential, typically the Buswell equation is used. For bioethanol production, limited oxygen is sometimes used to facilitate faster growth of the yeast and thus eventually higher production rates. In practice, biogas and bioethanol can be contaminated with various trace pollutants produced in the biological process, like for example hydrogen sulfide. Next to that, a small amount of heat is also generated anaerobically, but it is by far insufficient to produce work and/or power. Because of the presence of other impurities in biogas or bioethanol, the end product needs to be cleaned prior to producing work in internal combustion engines or power in natural gas-fired power plants. By using electrochemical conversion techniques, in this case fuel cells, it is possible to directly produce electricity while excluding the intermediate step of producing a mechanical motion to rotate the generator. In its simplest form, a hydrogen or fuel oxidation half reaction is catalyzed at the anode, due to which 1 electron is transferred into an electrical circuit. To close the circuit, on the cathode side, the electrons are consumed by a chemical reduction half reaction, which enables the transfer of a proton through the electrolyte. The potential difference between both reactions can then be harvested for electrical appliances. The anode, cathode, electrolyte, and current collector often need CRMs because of their catalytic and conductive properties. Of the many types of fuel cells, the solid oxide fuel cell can combine thermochemical gasification and reforming reactions with electrochemistry and is therefore considered the most compatible with most directly gaseous carbon-rich biofuels. Overall, it uses less quantity but more diverse and specific types of CRMs like nickel, yttrium, scandium, zirconia, and lanthanum, and even gold and platina to catalyze the thermochemical process and transport charge simultaneously at the higher temperature. To conclude, you now should be able to understand the basic steps needed for indirect and direct biomass to electricity conversion, can describe the roles of CRM in thermochemical and biological processes for biomass conversion, and lastly, you can explain the increased efficiency due to the addition of CRM in bioenergy conversions. In the next lecture, we will go into the water lab and go through 3 key practical steps to produce electricity from biomass using a biogas solid oxide fuel cell.